Dear students, in the last class we have studied splitting of d orbitals in octahedral complexes due to crystal field effects, and we also studied that these 5 degenerate d orbitals are split into two sets, one as T2g orbitals and the other one as EG orbitals. So we also studied T2g are comprising of dxy, dyz and dxz orbitals, and the EG orbitals, those are comprising of dx square, y square as well as dz square orbitals. Now today we need to study in what measurement the crystal field splitting is measured in octahedral complexes, or we can say that the crystal field splitting is measured by taking the difference between the two energy levels of T2g and EG. So therefore the difference or that energy gap is equivalent to delta O. So O is referring to octahedral complex. So this is also in general is measured by in terms of dq. So we can say that dq is also related to delta O, or in other words 1 delta O is equal to 10 dq. So therefore we can say that the T2g orbitals are taking an energy of minus 0.4 delta O or 4 dq. In other words, the T2 EG orbitals are taking the energy of 0.6 delta O or 6 dq. So this is the difference between the delta O and the dq. So therefore we have to study in what way these electrons are, or the d orbital electrons are entering into the T2g and EG. So any electron which moves to the orbital that prefers to go to the lowest energy orbital. So in this case the d orbitals are assigned, and therefore for the octahedral complex the lowest energy orbitals are obtained by T2g sets, or the highest energy level is given for EG sets. Therefore in a D1 system, or we can say that the D system with the one electron that prefers to move to the T2g orbital, that may be one of the T2g orbitals, and therefore that one electron is stabilized by either 0.4, that is the minus 0.4 delta O or minus 4 dq. So in one D1 system there is no problem in assigning any energy levels or any energy difference. But when it moves to the D2 system, where the two electrons are entering into the T2g orbitals, we have to have the two orbitals and the two electrons are moving to the two orbitals. That is to say that there are minus 0.8 delta O or 8 dq energy. So therefore in T2g the electron is again moving to the lowest T2g orbital, or in case of D2 system it is moving to the T2g orbitals. When it moves to the D3 system where the 3 electrons are placed, so these 3 electrons again prefers to move to the T2g orbitals only, because all these orbitals are of lower energy. So up to D3 system there is no problem. So when the D4 system is coming, or the 4th electron is entering into the d orbitals, there occurs a problem. So that's why all these parameters are studied under a group called as the crystal field stabilization energy. So I want to remind you that if electron in octahedral complex is moving to T2g, then that electron is stabilizing the complex. If the electron is moving to the EG orbital, which is of higher energy, and that destabilizes the octahedral complex. So therefore the stabilization and destabilization can be given by the crystal field stabilization energy, and it is abbreviated as CFSE. So therefore what is the definition of that CFSE? Or we can say that it is the lowering in the energy of the transition metal ion in a given ligand environment due to the crystal field effect. So therefore stabilization, crystal field stabilization energy is given by delta O and dq. Now again we shall come back to our original first discussion, that is about if the d orbital is having 4 electrons. So suppose if the 4 electrons move to the T2g itself, then one of the T2g orbitals must be paired up, or in other case if one electron that moves to the EG orbital, then all the 4 orbitals are remaining unpaired. So we can say that according to the Hund's rule, if the electrons are moving to the orbitals, then all the orbitals must be singly occupied. So in D4 system, we can study two cases based on crystal field splitting parameter. Okay, so we should discuss the first one, that is where the electrons are moving to only the T2G, and in that case the T2G is having the configuration that is T2G4. So in this case we can study the complex for the paired system, or one of the orbitals is paired up. So therefore this case will happen if the pairing energy is much less than the crystal field splitting. So again, to tell you, crystal field splitting is given by the energy difference between the T2G and EG. Say all the three electrons are filled in three T2G orbitals, dxy, dyz and dzx. Now the fourth electron, if that is again moving to the T2G, then say dxy is paired up. Okay, and this will happen when the pairing energy is lesser than this crystal field splitting, and therefore it pairs up. If this case is happening, then such complexes are called as low spin complexes. Low refers to number of unpaired electrons available are less, or it is, in other words, it is also called as strong field complexes. Strong field complexes are referring to the strong ligands. If the strong ligands are interacting with the metal ions, then it prefers the pairing of the electrons. So this is about the first case. Say the second case, where we can say that the fourth electron that moves to the EG in the sense it can move to either dx square y square, or it can move to dz square. Say all the three dxy, dyz and dzx orbitals are singly occupied. Now the fourth electron is moving to either the dx square y square or dz square, so that all the four orbitals are having the singly filled orbitals. Now when such cases will happen, say if the pairing energy is much higher than that of the crystal field splitting, or vice versa, that is to say that if the crystal field splitting is lesser and the pairing energy required for the pairing of the electrons is higher, then that electron moves to the EG orbital, say to the dx square y square. So if this is happening, then we call such complexes as high spin complexes, or the weak field complexes. High spin complexes are having a higher number of unpaired electrons, and these are called as the weak field complexes in terms of ligands also. Or we can say that in such a complex, so in such weak field complexes, the weaker ligands are approaching the central metal ion, so that they are giving rise to such a weak field complexes. So by this mean we can have the two complexes, or the two types of complexes, one as low spin, other one as high spin. Okay. Now the crystal field stabilization energy, what we have studied, that can be applied to these two low spin complexes as well as high spin complexes. So we can take a formula for that. That goes CFSE is equal to minus 0.4 into N of T2G plus 0.6 into N of EG orbitals in terms of delta O. So delta O is having either minus 0.4 or plus 0.6 orbitals, or plus 0.6 energy system. So therefore we can calculate the CFSE for D1 to D10 system by making use of this formula. So we have to remember that for the D4, D5, D6 and D7 systems, the four systems, we can apply both high spin configuration as well as low spin configuration. So a high spin configuration will always have unpaired electrons, or the higher number of unpaired electrons, but the low spin complexes, they are having the lower number of unpaired electrons, because most of the electrons are paired up in the orbitals. So that's why CFSE is applicable to octahedral complexes in this way. So we can recall that the T2G orbitals, that is dxy, dyz and dzx, they are taking either minus 0.4 delta O or minus 4 dq energy, or the EG orbitals, that is dx square y square dz square orbitals, they are taking the energy of plus 0.6 delta O or 6 dq. Or we can say that any electron moving to the T2g orbitals in octahedral complexes stabilizes the complex, or any electron that moves to higher energy Eg orbital that destabilizes the complex. So that's why the stability can be assumed for the octahedral complexes by taking into consideration the crystal field stabilization energy. So this is applicable to the tetrahedral complexes, then the tetragonal complexes, as well as the square planar complexes. So with this background, we can move to the tetrahedral complexes, where how the crystal field splitting is taking place and how the CFSE can be calculated for the tetrahedral complexes. That we shall study in the next class.